So the next item we're going to talk about are engine forces and measurement. How we measure the engine and how those relate to the forces it can output and can be subjected to. So the two measurements we're going to start with are actually measurements derived from things that we can actually measure with tools. Those are going to be the displacement and the compression ratio, but we're going to start more fundamentally with things that we can measure with tools. Those first two measurements are the bore and the stroke of the engine. The bore refers to the overall diameter of the cylinder. So when you look at a cylinder from the top, what you see is a circle, just a regular circle. And if you measure the widest point of that circle, what you get is the diameter. And in the context of our engine talk, that is what we refer to as the bore, the overall bore width. The stroke is the difference or the length of travel of the piston head when the crankshaft is at bottom dead center to top dead center. So you can see in this image at the bottom here we have the crankshaft throw is all the way at the bottom, and over here the crankshaft throw is all the way at the top. That distance that the piston travels from bottom dead center to top dead center is the stroke. What we can do is use these measurements to help us figure out how much the pistons displace, how much volume the pistons are able to move in the volume of air, and then also how much our fuel-air mixture will be squeezed when it's compressed during the compression phase of the four-stroke cycle. So if we were to take this side here, the maximum volume that the cylinder contains, and put that value over this value here, the volume at its smallest, that ratio, that relationship would give us some sort of ratio that tells us how much the mixture is squeezed. So 8.5 to 1 is an example of a ratio. This side is 8.5 times bigger than this side, and that can tell us a few things about the performance of the engine. The displacement overall is the volume that the piston takes up in its stroke, so a cylinder of height of the stroke, multiplied by however many cylinders there are. So in a single cylinder motor, all you need is the volume of a single cylinder over a single stroke. That's the displacement. If you have a 6-cylinder engine, you have to take that volume and multiply it by 6 to get the total displacement of the engine. This is just a couple of numbers that can help us parse out how powerful an engine might be, how big pistons and piston rings need to be. It's just a starting place when we talk about the engine. Okay, now what we're going to talk about are some of the forces involved. So one of the most fundamental and one of the most fun to say is torque. We're going to talk about torque. All torque is a twisting force. So when you think about a force, think about something like if you put your hand on a table and push down on it, what you're applying to the table and what the table is applying to your hand is a force. It doesn't mean that there's any movement necessarily. It just means that energy is being expended to apply some form of almost pressure is force over a surface area. But that act of pressing is the application of a force. In this example here, torque is actually rotational. So if we have a foot-long wrench and we apply a single pound to the end of that wrench, what we have here is 1 foot-pound of torque. And if we were to double that force, let's say we put 2 pounds on the end of this 1-foot wrench, what we have is 2 foot-pounds. We multiply those together and you get foot-pounds. So torque is a twisting force. Now the one that might be most familiar when it comes to talking about cars and machines is horsepower. So what the heck is horsepower? Well, fundamentally, let's start with the big word there, which is just power. What is power? Power is the force, like we were talking about before, a force that is multiplied by some distance. So again, let's say you have your hand and you're pushing on a table. You're applying a force, but if you're pushing down on a table and it isn't moving at all, the distance that you've covered is 0. So you have done 0 of what is called work. Work is a force applied over some distance. Now, if we take that same force that you're applying to the table and you apply it to the side of a book and you move that book a foot, now you have actually done some work. As an aside here, one of my favorite demonstrations that a physics teacher did in high school is he had a student, one of the like football players in our class, stand up, and the teacher picked up a chair and he handed the student a chair at like shoulder level, and so the student had to hold the chair at shoulder level, and then he said, okay, follow me. So the student followed him around the classroom holding this chair at shoulder level, and then when they got back to where they had started, they walked all the way around the classroom, and you could see on the student's face he was getting a little tired. The teacher took the chair out of his hands and then set it back on the ground, and he turned to the class and said, now, which one of us did more work? And the answer, of course, is that the teacher did more work by definition because he was the one who applied the force that actually lifted the chair and then set it back on the ground, whereas the student simply held the chair at the same level the entire time. So although he was applying a force, it didn't cover any distance, thus no work was done. Kind of a confusing example there, but interesting when you think about it mathematically. So we take our force and we cover some distance, but to get power, we need to include the element of time. We divide that force that we've applied, the distance that we've covered, we divide it by the overall time it took. So if we go back to our book example, if you are able to apply that force to the side of a book and it slides 1 foot and you accomplish that amount of work in 1 second, you have exerted or you have expended a certain amount of power. Expressed is maybe a better way of saying it. Expressed a certain amount of power. Now, if you do that same, you apply the same force over the same distance, but you do so in a much shorter amount of time, what you're expressing is more power. So instead of it taking a second, if it takes half a second, you're actually moving that book a lot quicker across the table. So there's more power involved. So imagine, if you will, 2 cars, same weight, same size. The one with more horsepower is going to be able to move that same weight car over the same distance much more quickly because they're able to exert more power. How does this relate to horsepower? Well, 1 horsepower is calculated to be 550 pounds of force multiplied by a single foot, so it covers a foot of distance over the span of 1 second. And remember that 550 pounds of force has to be exerted in the same direction of the movement. And so you might see a diagram where a horse is lifting some kind of weight via a pulley assembly off the ground. But this right here is the equation where we can calculate what an actual horsepower is. And I've included a video on the resources portion of the lecture so that you can relate it. I like having a visual way, but this is the mathematics. I also just like having like a visual representation of an animal that goes with it. When you think about what watts are, or kilowatts, that's the metric way of measuring power. It's hard to visualize, but it's kind of easy to imagine like how much power a horse has with all of its muscle versus like a watt. So that's just kind of a funny aside for me. Okay, up next, what we're going to talk about, the next section actually, we'll be talking about diesel engine operation and diagnosis. Thank you for listening.